Alrighty, welcome everybody to our next talk in our speaker series. This talk is on the James Webb Space Telescope. For those of you just joining, feel free to, if you're in Zoom, feel free to introduce yourselves and where you're from, as is our tradition here with Raskin Sky News. A note for those who are joining on Zoom, if you would like to talk to everybody and not just those of us on the panel, make sure to change the little bar at the top of your chat window from hosts and panelists to everyone. Alrighty, I'm going to hand things over to Alendria to introduce our speakers.
Great, thank you, Jenna. Yes, so welcome everybody to this speaker series talk. And today we are, the subject of the talk is the James Webb Space Telescope and Canada's role in the exploration of the universe. For those who don't know, I'm Alendria. I'm the editor-in-chief of Sky News magazine, and my co-host tonight is Jenna Hines, outreach coordinator for the Royal Astronomical Society of Canada. And the James Webb Space Telescope is the most complex and powerful space telescope humanity has ever built. Poised to launch this December, its array of 18 hexagonal mirrors function as a single mirror 6.5 meters across, allowing us to observe farther into the universe than we have ever seen before. And this historic project is an international collaboration between NASA, the European Space Agency, and the Canadian Space Agency. So what is Canada doing? To answer this question tonight, we have Jean Dupuis, the senior mission scientist in space astronomy at the Canadian Space Agency, and Nathalie Ouellette, the coordinator of the Exoplanet Research Institute at the Université de Montréal, and the scientific coordinator for the James Webb Space Telescope in Canada. And just some housekeeping things for those of you who entered a little bit later. If you have a question, you can put it into the Q&A. It should be down on the bottom of your screen there. And if you would like to use the chat function, feel free. But don't forget to use that drop-down menu and choose everyone if you would like everyone indeed to who registered for this talk to see your message. And if you are on YouTube, joining us on YouTube, you can drop your questions in the chat there. We'll try to monitor that window as well. And so without further ado, I will pass the mic on to Jean. So thank you both for attending and joining us here tonight, and take it away.
Well, thank you so much. I'm really honored to give you this presentation tonight. Thank you very much for the invitation. It's our pleasure to talk to you about the James Webb Telescope, Canada's role in the exploration of the universe. Astronomy, I mean, as is...
Jean, you just have to share your screen real fast.
Oh, sorry. Sorry about that. Okay, share. Okay.
Perfect, thank you.
All right, sorry about this. Okay. So astronomy is a science that is fascinating everybody. You're likely to know that astronomy is a great spark to get people, especially children, interested into science. Astronomy is one of the oldest science practiced all around for millennia. Amateur astronomers only need a dark sky and their naked eye, binoculars, their telescope, to see amazing things on the clear sky. Over time, astronomers have developed more and more sophisticated techniques and methods to collect information about planets, stars, and galaxies surrounding us. We have some ground-based telescopes, such as the Canada-France Hawaii telescope, and other large telescopes all around the world that are learning us new things about the universe, collecting data every night when the weather permits. The second way to learn about the universe is to send telescope in space, such as the Hubble Space Telescope, which is probably one of the best known space observatory that has been in operation for now over 30 years. It has more or less, say, revolutionized our understanding of astronomy, and gathered so many beautiful images as those shown on the left of the slides. It has contributed to measure the age of the universe, measure the expansion rate of the universe, discover dark energy, and many more discovery. Too many, I guess, to enumerate tonight. The telescope inside Hubble is, reasonable, respectable size of 2.4 meters wide, which had to be adjusted, as you know, due to some optical flaw, unfortunately. There were like several repair missions or servicing mission allowed to place new instruments during the lifetime of the telescope, which make this a very unique facility that is still being used by thousands of astronomers all over the world. It's a good thing that it was in the low Earth orbit, so it could be maintained. There are, of course, many more space telescopes that we don't hear as much, observing the X-ray, some observing UV, some observing IR, like mission dedicated to the cosmic microwave background. We're really living in the golden age for astronomy, but I would say especially for space astronomy. Like take this opportunity to mention that Canada also is an important player in space astronomy. We have our own space telescopes, such as MOST, the Microvariability and Oscillation of Stars telescope, the NEOSat, which also is another micro satellite dedicated to the study of near Earth objects, such as asteroids. And it's also used right now to do astronomical observation of stars, mainly exoplanets, with exoplanets. Yeah, so in astronomy, I guess the larger the telescope is, the more light you're able to collect. So astronomers, as you know, love large telescope. So that's partly why I think Webb was designed, is that just with in mind of having this larger collecting area that will open us the door, or the more distant corners of the cosmos. I mean, astronomers were truly forward-looking, because they started thinking about James Webb a long time ago. This was like a truly, I would say at the time, innovative idea to go on with this super ambitious project. So we're showing here a comparison of Hubble with James Webb. You see like this mirror, which is a bit of a peculiar shape. It's made of 18 hexagonal segments. So it's a segmented mirror. So this was like really, we'll say, forward-looking to think about that at the time. So James Webb, I think, will truly represent a new chapter in astronomy. I mean, its size and complexity, as we'll discuss a bit later, are simply unprecedented. So the project is the fruit of an international collaboration between NASA, ESA, the European Space Agency, and the Canadian Space Agency, which makes it like a truly exciting opportunity from a Canadian point of view. Webb is a major astronomy mission to which Canada is contributing hardware. And in exchange of its contribution, it's receiving an appreciable amount of observing time for Canadian astronomers. Because of its massive golden mirror made of 18 hexagonal segments, it will be the most powerful space telescope ever built. The 5 layers sunshield that you see over here is as large as a tennis court. In fact, Webb is so large that it has to be folded like an origami to fit inside the Ariane 5 rocket that will launch it from Europe spaceport located in Kourou, French Guiana. After it launched this year, planned on December 18, Webb will travel away from Earth, deploying its sunshield, which has an SPF factor of over 1 million. It will be used to protect Webb's very sensitive instrument from the intense heat of light from the sun. The temperature difference between Webb's hot side, the sun exposed side, and the cold side in the shadow of the sunshield will be over 300 degrees Celsius. So we see here the deployment of the sunshield. In fact, for the first 29 or 30 days, often called 29 days on the edge, there will be the deployment of 40 major systems. Just the sunshield, in fact, required 115 mechanisms to properly release over the course of a few days. So this will be, I would say, a scary phase of the mission. Some people will lose sleep over it, I can promise you. The Webb mirrors will deploy, and the telescope will be ready for the initial testing phase that we call the commissioning phase that will last about 6 months, during which the telescope will be aligned and all the instruments will be activated and calibrated. So there will be a very busy phase where every observing mode will be checked, tested. There will be some tweaks done to the instrument. It will be a lot of fun. Really looking forward to it. So Webb, as I just told you, Webb will unfold very slowly as it travels to a point in space called the second Lagrange point, or L2, located at about a distance of 1.5 billion kilometers from Earth. So Webb will be orbiting around L2 in what we call a halo orbit. Yeah. So considering that Webb will be so far away from Earth, it has to be like perfect before launch. It explains partly why it took so long to be ready. So it had to be tested and retested, deployed, and they tested that sunshield like several times, and so a lot of care was taken to make sure James Webb will work properly. With Webb, we'll study every phase in cosmic history from the first light after the Big Bang to the formation of stellar system hosting planets that maybe will support life. the evolution of our own solar system. So it will be a very broad range of science topics will be studied with James Webb. Basically, every domain of astronomy will be studied. So it will, I mean, truly open a new chapter in our understanding of astronomy, the universe, and our place within it. So James Webb initially was mainly, let's say, conceived to study like the early universe. It would do more, but that explains partly why it's optimized to observe in the infrared. Like it's the first generation of galaxies that are thought to have formed maybe a couple of 250 million years after the Big Bang. I thought to be like very bright in the UV and in blue light. But the light from these galaxies, since they were formed like quite early in the age, in the evolution of the universe, has traveled very long distance, as you can imagine, before they reach us, and James Webb eventually. And the light has been stretched by the cosmological expansion of the universe. And there's been stretched so much that that light is now like in the infrared. So that's partially why Webb is optimized to observe in the infrared. As you know, there are many kinds of light around us. I mean, the rainbow of light we can see with our eyes, but there are other types of radiation like X-rays, infrared radiation, microwaves, radio waves that are not visible to the human eye. That partly motivated, we'll say, space astronomy, the fact you have to be outside of the atmosphere to be observed to detect X-rays and hard X-rays, even infrared. You can do some infrared from the ground, but it can be better be done from space. And also to get like very nice quality image, it's better than to have the atmosphere. So Webb will collect infrared light that cannot be perceived by the human eye. Also, certain phenomena, certain physical phenomena or object will emit light, preferably in the infrared, like from cold object like planets or cold stars. So also one advantage of observing in the infrared is that infrared can penetrate to cosmic dust. And we show such an example here in this in the figure where these are Hubble observations of the Eagle Nebula in the optical on the left and the infrared on the right, where you see like more like stars in the infrared image because there's less absorption by dust in the cloud. And so that sort of gives you an idea of the different perspective that IR or infrared observation gives you of the astronomy. So Canada, so in order to become a partner in that mission, we have to provide like a major hardware contribution. So we have contribution. Canada has contributed what we call a fine guidance sensor, or the FGS, and the near infrared imager and slitless spectrograph, NIRIS. These are extremely sensitive instruments. Again, I remind you that contributing these instruments means that Canadian astronomers have allotted time for observation with James Webb. It's very precious. What will these instruments make? The Canadian FGS will allow Webb to determine its position in space, to help locate and track the celestial targets it will observe, and it will, more importantly, help the telescope remain very steadily locked with extremely high precision on specific targets on what we call guide star. The FGS will play an important role in all scientific observations to be made with James Webb. It will always be used in parallel with all observations by ensuring the collection of clear and detailed image. What will NIRIS do? So NIRIS, as the name says, an imager in the spectrograph. That will be used mainly. There's a lot of interest in using NIRIS to study exoplanets. Like the picture shows an exoplanet transit, and NIRIS will allow to do like spectroscopy of exoplanet during such transits, and allow us to measure the chemical composition of exoplanets. Yeah, so by measuring the chemical composition of exoplanets, we'll be able to detect specific molecules in their atmosphere that could be possible, like biosignature, like water, carbon dioxide, methane, and oxygen, and we'll see if it's a match. It will also allow us to like better understand the properties of exoplanet. It's like a very fundamental contribution. It will do more than exoplanets. Will also be used to observe like very distant galaxies, like to do like deep spectroscopic observation of the galaxy, very complementary fashion to what will be done with other instruments aboard James Webb, and Nathalie will talk more about that. But there's also a very niche application called the AMI mode. It's an aperture. AMI means aperture masking interferometry. So that will allow to do very high spatial resolution observation of objects, and that will allow us to find new exoplanets, for example, orbiting stars, and characterize the nuclei of active galaxies and more. And so NIRIS will be like a superb instrument. We're very proud of it. So in summary, Webb will represent the beginning of the new chapter in astronomy and promise to really deepen our understanding of the cosmos. Webb has 4 major science objectives: the worlds, the star life cycle, the early universe, galaxies over time. And Nathalie will talk to you more about that in the second half of this talk. So again, thanks to Canada's contribution to the mission, Canadian researchers will have access to observation time to take part in these unprecedented discoveries. Thank you very much. So this concludes my part of the talk.
All right. So if you can just stop your screen sharing, I will pick up my half now.
Yes.
All right, perfect. Thank you so much, Jean. Can anyone confirm that they can see my screen?
Confirmed.
All right, perfect. So yeah, Jean went over what makes this mission really special, really exciting, and that Canada is part of this mission, which was not formally the case for Hubble. So it makes it really, really an exciting time in astronomy to be Canadian. And I'm hoping just one of the first missions where we're collaborating with NASA at this level. So Jean briefly mentioned these 4 chapters. These are the 4 big scientific goals that NASA and its collaborators have put out for Webb. So I'll be going over these in more detail, and specifically, I'll be talking about the Canadian science and Canadian astronomers that will be studying these different topics and what programs they will be leading and what kind of time they'll be getting on James Webb. So we'll be talking about other worlds or alien worlds, whichever you prefer, the stellar life cycle, the early universe, pushing how far back into the universe we can see, because it was, as we know, astronomy is like looking through a time machine, and studying galaxies over time as well. So before I jump into this, I can briefly mention that in exchange for the Canadian contribution of the NEARES and FGS instruments, Canada will get at least 5% of time on James Webb. And that's a pretty good deal because we paid for about 2.5% of the total budget. That was our contribution. So we kind of got away with getting twice the amount of time if we were just doing a one-to-one trade there. And of course, some of that is going to be done through a competitive process. Every year, astronomers submit telescope time proposals to try and say, my science is better than all the other science, and you should give me time on Webb. And we did that for the first year, cycle 1. We concluded that process. We submitted a year ago. The results were announced in March, and we're prepping for those observations during the first year of operations of Webb. So those are just general observer programs, or GO programs. But we also have 450 hours of what we call guaranteed time observations, or GTO. And this is a direct exchange for the contribution that Canada has done through its instrument. And this time is spread out amongst a few different programs, 2 really major ones that I'll mention. The last type of program I wanted to mention is called ERS, or Early Release Science. These were programs that were selected for a few different reasons. First of all, these will be the very first scientific programs that will get time on Webb. And one of the first things we want to do when we have Webb online is test out all of its instruments, all the different modes on the instruments, to make sure everything works well. So these ERS programs will do just that. They will test out all of these different instrument modes. And we also want this data to go back to the community as soon as possible. So the people leading these ERS programs committed to making these data public very early on, and even giving support to the community to help people analyze these data, reduce these data, and use these in their science. So they're very altruistic programs. Of course, the people that are leading these programs have a good reason to get the time too, but they are the reason why they're going to get the time at the very start. So the first scientific goal that James Webb will have is to study other worlds. And when we think of other worlds, I work at the Institute for Research on Exoplanets. Of course, we think a lot about exoplanets, but we can start closer to home. There are a lot of interesting worlds inside our solar system that will be great targets for Webb. There are some that we can't study just because they're in the inner solar system towards the sun. And if we were to point Webb towards the sun, we would fry the whole thing. So Venus, Mercury, the Earth, and the Moon are off limits, but we can look at the outer solar system, especially Uranus and Neptune, which have been a little bit neglected by some explorer probes. They will be really interesting targets. We'll also be looking at some really interesting ocean worlds, or ice moons, around some of the gas giants such as Jupiter and Saturn. And this is a picture of Enceladus, which is a moon around Saturn. It is a small moon that is totally encrusted in ice, and there's a liquid ocean underneath. But we can sample that liquid ocean via cryovolcanoes, or ice volcanoes, on this ice crust that eject out some of that liquid water ocean. And Webb will actually be able to study the light streaming through these jets, these water ejections coming out of Enceladus, and it'll be able to determine the chemical composition of that liquid ocean and potentially find out more on whether the ocean on these ocean worlds are habitable or potentially even have biosignatures. But of course, we're also interested in looking out to farther worlds, farther alien worlds, such as exoplanets. So many of you might know that the way that we tend to find exoplanets, the most efficient way to do so is what we call the transit method. So when an exoplanet passes in front of its star, it blocks out a part of its light. And depending on how much of its light is blocked, you can get information about the size of the exoplanet, how long it takes for it to transit over the disk, also tells you about the period of its orbit, the distance of that planet from its star. And that's really great for detection, but there's an added bonus if on top of the solid part that's blocking out the starlight, you have a thin, translucent or transparent atmosphere. And atmospheres to us is very interesting as we're looking for alien life. So when these exoplanets transit over their stars, the starlight will stream through this atmosphere, and some of the light from the star will actually be absorbed by different chemical components, molecules, and atoms inside of those atmospheres, such as water vapor, carbon dioxide, methane, ozone. And so by looking at the light streaming through these atmospheres, this is a technique called transit spectroscopy, we can actually determine the chemical composition of these exoplanet atmospheres and maybe find out if they're habitable or find signs of alien life. This would be like a fantastic, really ground-shattering discovery, of course. And NIRS is actually a very, very well-designed tool to do this transit spectroscopy in one of its modes. So I can mention a few different programs that will be looking at these other worlds led by Canadian scientists. And one thing that I'm really happy about, these are the people that are leading these programs, and you'll see a lot of young faces. So we actually have a number of programs, proposals that will be getting time from Webb during the first year, led by graduate students. So this is really a telescope that will be great for the next generation of astronomers. So I mentioned GTO programs. This is the time that Canada has guaranteed in direct exchange for the Canadian instrument. There were two really big ones. The first one I can mention is NEAT. This is led by Professor David Lafrenière, who is a professor at the University of Montreal. And we're going to get for this program 204 hours to study the chemical composition of exoplanet atmospheres. And there are lots of interesting targets. Maybe you know TRAPPIST-1, that's going to be one of the targets. 7 exoplanets, all Earth size. Many of them might have an atmosphere, 3 or 4 of them in the habitable zone. So really promising targets there. So that's one of our 2 major GTO programs. On top of that, there are several other GTO programs and GO programs that went through that competitive process for the first year for a total of 244 hours in the first year or so of Webb's operations, working on rogue planets, planets that no longer are orbiting a star, brown dwarfs, sort of those weird objects that are really, really big planets or really small failed stars, protoplanetary disks. And this will be done partially using the AMI mode, aperture masking interferometry mode that Jean mentioned. Will be able to take real pictures of solar systems that are being formed. Trans-Neptunian objects, so objects that are beyond the orbit of Neptune, such as Pluto and all of Pluto's buddies that sort of like ruin Pluto's chance of being a planet. They'll be interesting targets as well. And of course, lots of interesting programs on exoplanets. The next big scientific goal that Webb has is to study the stellar life cycle. And this is a really gorgeous image taken by the Hubble Space Telescope that really exemplifies the entire life cycle. So in the red, you have a nebula where you have lots of star formation that is happening. So you can actually peer through the cosmic dust using infrared light with Webb to look at these stars that are being formed within these stellar nurseries. And on the blue part there, you have a planetary nebula, the leftovers of the death of a sun-sized star with the white dwarf at the very center. So we're really interested in studying stars across their entire evolution and lifetime. And a few programs that I can mention, I mentioned these ERS programs, the first programs that are going to get time on Webb because they're going to be giving this data back to the community really fast and testing all the different instruments on Webb. We have one program that is co-led by a Canadian, Else Peters, who's a professor at Western University, and she will be studying the environmental effects of massive stars, stars that are much bigger, much more massive than the sun, and how they affect their environment. So these stars inject immense amounts of energy back into their environment, such that they create what we call photodissociative regions. Basically, that energy is so intense and violent that it changes the chemistry of the environment around it. And we actually have a photodissociative region in the Orion bar located inside the Orion Nebula. So led by Else Peters, this team will be studying PDRs, or photodissociative regions, trying to make a blueprint of it and a model of it to sort of like put a baseline on how all of these studies of these really important objects can carry forward in the future using Webb and other instruments as well. So on top of that, studying the stellar life cycle, there are several other GEO programs through that competitive process that I mentioned for a total of 53 hours, studying all kinds of things, including kilonova explosions, which is when you have two neutron stars that smash into each other, they blow up, and that explosion is so intense that you can actually create very, very heavy elements on the periodic table. So super interesting. White dwarfs, which was at the center of that planetary nebula in the blue, which is sort of the corpse of a star after it dies off, and star formation regions in nearby galaxies as well. A really important part of Webb will be trying to push how far back we can look in the universe. So really trying to study the very, very early universe. So how far have we been able to look without Webb at the early universe? So obviously, we've always been trying to push that back. With our ground-based observatories, we have to sort of like limit ourselves. We're dealing with an atmosphere that's blocking out some of that light. We can't really look through infrared light. So when we started sending things into space that had large apertures, we could look quite a bit far back. And you might be familiar with different series of Hubble deep field images that were really trying to like look at these very, very distant galaxies. So with Hubble, we were able to push that back to around 500 million years after the Big Bang. With Webb, we'll be able to push that even further back to about 200 million years after the Big Bang. Now, people often think 200 million years, that sounds like a really long time. 200 million years ago, we had dinosaurs running around on the Earth. That seems like not that soon after the Big Bang. But 200 million years relative to the entire history of the universe, which is about 13.7 billion years, is actually quite quick. So if you took the entire history of the universe, you put it on a calendar year and you put us, modern time, on December 31st at midnight, or just about to turn midnight, looking back as far back as Webb can look is like looking back until January 6th in the year you're currently in. So you're looking really far back at the beginning of the year. So there, we're hoping to look at the very first galaxies ever created after the Big Bang. So that'll be really fascinating. And that'll help us study galaxies over time, which I'll mention in a moment. So yeah, we're trying to really push back the redshifts of these galaxies that we're looking at. So the last scientific goal that Webb has is studying galaxies over time. So not only do we have to contend with all these galaxies that are really, really far back, really, really faint, and we have to use special little tricks like looking in the infrared because their light has been redshifted because it has traveled such a large distance. We also have to use weird tricks like gravitational lensing, where we're hoping that a big mass is between us and these distant galaxies, such that the mass in between acts like a lens and focuses and even brightens these faraway galaxies. But galaxies over time have lots of things that affect their evolution. These galaxies are colliding together, they're merging, they're affecting each other, their environment affects them as well. And depending on which era of the universe you're looking at, galaxies are evolving at different rates, different states. So we have lots of stuff to look into. And Webb will be able to do that all the way from far away distant galaxies to very nearby galaxies such as Andromeda and the satellite galaxies around the Milky Way. So some of the projects that I can mention that are going to be done in Canada about galaxies. There's the other GTO program. So we mentioned NEAT, which will talk about the chemical composition of exoplanet atmospheres. The other GTO program, the large one, is Canucks, another very fun name, 199 hours. It'll be studying those very distant cluster galaxies that I mentioned, some of the first galaxies ever created, using gravitational lensing, as I mentioned. So that'll be a really big program, and it'll be able to use a mode on the nearest instrument, the Canadian instrument, that allows you to take simultaneously thousands of spectra at a time. So you'll be able to look at lots and lots of galaxies in a single galaxy cluster in one observation. So taking all those spectra together, that'll be really, really fantastic. On top of that GTO program, we have several other GTO programs and GEO programs for a total of 83 hours, looking at galaxies evolving over time. Some topics include the high resolution imaging of nearby galaxies. So not only spectroscopy, but we'll also be doing imaging, galaxy formation and evolution, and the importance and effect of supermassive black holes at the center of these galaxies as well. So with all of this, I hope we've gotten you really excited that Webb is the most complex and powerful space telescope ever built. There are other things that are really complex. CERN, of course, is complex, but they didn't strap CERN to a rocket and then launched it into space and then launched it 1.5 million kilometers into space where no one can touch it. I'm not saying we're better than CERN or anything, but like it's a very, very intense mission that we're putting together here. And we're very excited. Canada has a strong contribution here, and we're hoping that we can take this expertise, really have fantastic science coming out of Canada using Webb, and then it'll just lead to more exciting projects in the future. So the presentation that we gave you today is sort of a teaser about lots of different things going on with Webb. There's lots of interesting content from RAS that will be coming out in the next few weeks leading up to launch and after launch. To give you more tidbits, you'll be able to meet some scientists, some engineers that are working on the mission. Very exciting. But really, one of the reasons why we wanted to talk to you today is because we want to highlight the importance that the amateur astronomy community has in propagating the message that Webb is almost here, it's super exciting, and Canada's part of the mission. So we hope that you will feel inspired, number one, of course, and number two, that you will go online and find all of our resources we put together and feel maybe like you have the toolkit necessary to talk to your friends or your family or local classrooms or science centers about Webb as well. We know that you are really, really great ambassadors for astronomy in general, and we would love for you to carry that forward with Webb as well. And if you do social media, you can tag us at any point. If you have media requests or you have any questions at all, you can contact us at this email and this telephone here. So we're happy to take your questions now, and yeah, reach out and just spread the Webb love. Thank you so much.
Thank you so much, Natalie. Really appreciate it. If you could stop sharing your screen for a minute so that we can see everybody, that would be awesome. Thank you so much. So thank you both to Natalie and Jean for your contributions and for your amazing presentations on this telescope. We have a bunch of questions from our audience, so I'm going to jump right in. The first one I wanted to ask was from Swapna, which is, once it's launched, how long will it take the telescope to get to its place where it's going and be fully operational? And when will Canada start getting the data back from the telescope?
Did you want to take this, Jean, or?
Yeah, well, I can take the first. I guess to get to L2 will take about a couple of weeks, if I remember correctly. And as I said, it will take 6 months to, I guess, do the full commissioning of the observatory. We'll start getting some data before, we'll say, the 6 months as the instruments are commissioned. We'll probably start seeing, we'll say, image probably during the last couple of months. Do you agree?
Us on the inside or the public?
On the public.
Yeah, so in all likelihood, the publication of the first images, which we call EROs, or early release objects, which are top secret. I don't even know what they are. In all likelihood, we're looking, if everything goes well, around June or so, at the end of the 6-month commissioning period. And afterwards, in terms of getting science, as soon as commissioning is done, we start science operations. Yeah, some of the data will be available publicly immediately. Basically, when a telescope is done taking your data, there's a little bit of reduction that happens, but you receive it as the person that leads the program almost immediately.
Yeah, so the GTO, what we call the GTO, the guaranteed time observation, will be obtained, I think, mostly during the first year of James Webb. So the guaranteed time to the Canadian science team, I think we should have some data quite fast, I will say, during the cycle 1. And I think the early release science observation, ERS, also will happen really soon during the mission. The idea is to have like a rapid release of these data to, I guess, to help the astronomers all over the world to, I guess, to analyze their data, provide some typical data set for each of the instruments, some, we'll say, software or data reduction recipes, software that will assist everybody. So like these programs are made for the benefits of the overall community.
Awesome, thank you so much. This is an immediate follow-up question, which I'm pretty sure you answered, which is what will be the first observation? And as far as I know from what you said, that's top secret, right?
Yep, top secret.
Yeah.
Perfect, good to know. I am looking forward to finding out what it is, and I'm sure everyone in the chat is as well. There's a question about Canadian contributions. How long ago were the Canadian components, the FGS and NIRIS, completed and ready for installation on James Webb?
Quite a long time ago, actually. They were delivered in 2012 to NASA. Yeah. So at the time, it was supposed to launch earlier. So there was I will say, a lot of pressure to deliver.
Yeah.
So, yeah.
But them getting it, it was always, you never want to get your components like, you know, a week before you launch. There was very thorough testing that was done on each individual component.
As well.
Yeah.
And our instrument was one of the first to be integrated in what we call the ISIN, the instrument science instrument module. So
yeah,
so
if you
had
look
to
at
deliver early. Oh, good, it's a good idea. Yes.
Yeah. If you look at where Webb is, oh my God, the green screen is ruining everything. You have the mirror there, and this box in the back is where all the scientific instruments are put. So the way that this is configured, what's at the heart of it is FGS NIRIS. So we had to be ready first because everybody else like got piled on top of us.
Yeah.
It's funny, I didn't realize that. I didn't realize that we were the core component. Could you touch on why there was such a long delay in the James Webb?
Sure, I can address this. So there are a few different historical reasons that Jean can also mention related to like budgeting and having to have budget expansions approved and everything. But essentially, we had to be extremely conservative in our testing. So the testing was done very, very thoroughly. But every time that there was a little snag or something that seemed amiss with the testing, it put the schedule back because you had to come back and make sure that whatever that snag is was fixed. And the reason why we had to be so conservative is because, well, number one, it's a very, very complex mission, of course. But number two, we don't have any second chances the way that we did for Hubble. If something breaks or doesn't work or doesn't deploy, and God knows there is an enormous amount of things that could break or not deploy, then it just is the end of the mission before it even gets started. So the schedule was kept very, very conservative to make sure that any single possible issue could be fixed before launch.
Yes. exactly. And also those tests had to be like cryogenic, so you had to test the instrument at the temperature at which it will be operated in space. And I think, if I remember correctly, tests were added at some point. I think some people consider that, oh, maybe we're not testing enough, and so some like test cycle were used, and that increased time. And so yeah, it's
on that note, and I expect the answer will be similar to what we just heard, there was a question about contingency plans. Are there contingency plans developed in case Webb has issues in its deployment or throughout its expected lifespan?
So there's a number of redundancies. In general, the deployment mechanisms, if the first layer fails, then there's a redundancy there, but there's not infinite redundancy. So at some point, if a single point failure and its redundancy fails, then there is no second chance. And we try as we might, want to sugarcoat it and everything, but like that is the reason why there were those delays and why we had to be so conservative, because at some point, if there is a critical failure that happens with Webb, we can't send a mission out to fix it.
Perfect, thank you. Always good to be cautious as someone who does not build expensive telescopes.
yes.
So we had a couple questions about sort of like the location of the telescope and why it was chosen. What is the significance of the Lagrange point from the perspective of James Webb, of the Webb telescope, and what were the reasons that it was chosen?
Yeah, I could start, Nathalie, and feel free to add. So it's mainly for, I would say, thermal reason. I mean, it's an infrared telescope. We want to do very sensitive observations, so the telescope itself has to be kept like very cold, and the instrument as well. So the best way to do that is always have the sun and earth and moon beyond you, and L2 is, I think, a place from which can be done, I think, very well. Other observatories have been operated successfully from L2. NASA has operated, WMAP,
Spitzer, Kepler.
Well, Spitzer and Kepler were not quite at L2, but were on Earth trailing orbits, a bit different. But Planck, ESA has operated Planck Herschel from L2. So it's mostly for thermal reasons.
Yeah, and one point that I can add is for those of you who aren't familiar with Lagrange points, essentially in the Sun-Earth system, there are 5 different points that are gravitationally stable, where an object can sort of like stay there and not really have to like use up much energy to stay at that point. Lagrange point 2 is what we call a quasi-stable orbit. So Webb has a quite large radius around that point in orbit, but the amount of fuel required to keep it there is relatively small. And fuel is actually what limits the lifetime of the mission. So the more you can stretch out your fuel consumption, the longer the mission can last. So it's one of the advantages of staying close to these Lagrange points too.
Awesome, thank you so much. There's a question about the shields. Or there are a couple questions about the shields. One's to do with the view. One is to do with what it shades from. So does the shield shade everything on the telescope, including the secondary mirror? What's shaded by the shield?
So I can show my little thing here, if you can see it. Okay, I'll put it in front of my face. That seems to work. So yeah, you have the shield there. So if my fist is the sun, this is always going to be the configuration of Webb. So on this side here, you have the solar panels, which makes sense because you want them to be getting sunlight. You have the communication array as well, because that'll be pointed towards the Earth. And on this side, what you're keeping cool is both mirrors, secondary and primary mirror, and the instruments at the back. So this is the cryogenic part here.
Perfect. There was another brief question about whether or not it's protected from cosmic radiation, or is it just protected from like infrared light?
I don't know if you wanted to take this, Jean, or
I'm not sure I understand the question.
yeah. So the sun
cosmic
shield
rays.
Yeah, I think
right.
that's what they meant.
Cosmic rays. Yeah.
Cosmic
so
rays.
I mean, cosmic rays, extragalactic cosmic rays. They're like there are two big sources of radiation in space. You have solar radiation. You have cosmic rays. Cosmic rays come from any which direction. So the sun shield won't necessarily be protecting the mirror or anything. What's in here, basically all the components, the lenses, the optics, the detectors, they've all been tested to not be damaged by cosmic rays. But cosmic rays is a reality of life when you're doing any kind of astronomy, and you end up with things like little traces, like these little lines that are going across your images. You end up having to subtract that in your data reduction. But yeah, everything has been like tested, radiation tested, to make sure that it can survive cosmic rays, essentially.
Awesome, thank you. And one last one to do with the heat shields. So since the heat shields take up nearly 50% of the view, one of the questions here was whether or not we'll be able to see towards the sun or Earth. Nope. Yeah.
No.
But then could you also touch on, how the orbits work? Because it doesn't mean that half the sky isn't visible. It just means that we see it at a different time of the year, right?
Yeah.
Yeah, it's not half the sky. So we call this the field of regard of the telescope. And essentially, again, if the telescope in my fist is the sun here, as the telescope orbits around the sun, it like ends up having access to that side of the sky the other time of the year. In terms of trying to look closer to the equatorial plane, there is a little bit of leeway. The mirror can tilt back a little bit like that and a little bit like that to look a little bit further in or a little bit closer to the equatorial plane, but there's a limit as to how much it can tilt back before the sun shield no longer effectively protects the telescope. So that range is what we call the field of regard of Webb.
Awesome, thank you so much. I am going to stick with one last question because we're getting close to an hour. The last question that I have for you is, what are you two doing on the launch day?
Oh, Jean's answer is much more interesting than mine, so I'm going to let him answer.
Well, I will have the great privilege of being able to attend the launch in Peru. So I'm so excited about that. I can't tell you how much. So in principle, I shall go there along with a couple of colleagues from CSA and the PI from the Université Morel, René Doyon, and so it will be, I think, a thrill of a lifetime. Yes,
You'll take lots of pictures for us?
I will take a lot of pictures, I promise, movies.
Good.
Yes.
As for me, I'm going to be holding down the fort in Montreal, which is sort of like the scientific center in Canada. A lot of my colleagues will either be at Kourou or at Baltimore at the Space Telescope Science Institute, which is the operations center for both Hubble and soon Webb. But there'll be some activities going on here and media interest in Montreal and in Canada. So I'll be holding down the fort north of the border.
Those are both awesome plans. I mean, they sound, it's going to be so exciting. And Jean, you're lucky to get to be there. And Natalie, you're lucky to get to share the excitement with everyone across Canada. Thank you both so much for being here and for sharing so much about this amazing telescope. Before we sign off for the night, there are a couple housekeeping things that Alendria and I wanted to share. Alendria, you want to go first?
Sure. Again, yeah, I just wanted to thank you both for being here. I'm sure that we'll be among the media interest at Sky News that'll be reaching out on the day of. I'm just going to share a couple links in the chat boxes here. First off, it's to the e-edition, the link where you can find the e-edition of Sky News. Dan Falk is actually in the chat tonight. He's here at the presentation, so thanks, Dan. Dan wrote the article that's on about the James Webb Space Telescope in the most recent edition of Sky News, and he actually spoke to Natalie for this article. Thanks, Natalie. And yeah, so you can find that there. I also wanted to share with everybody the upcoming speaker series talks, just the list, and if you wanted to register for any of them. We have 2 coming up. One is about hunting exoplanets from your backyard. So if you don't have access to the James Webb Space Telescope, you can set up your rig if you have one in your backyard, and Laurie Sibyl can give you some advice on how to do that. The other talk that we also have going on is going to be Mi'kmaq Moons. It's with Kathy LeBlanc, her niece Holly, and Dave Chapman. And you can read more information at the links that I am going to post in the chats. And with that, I'll again thank you so much for being here and for speaking with us tonight. And back to you, Jenna.
My last thing is just to mention that if anyone who is one of our outreach volunteers here at RASC, or with anyone who's interested in sharing the James Webb Space Telescope with anyone in their life, students, children, friends, relatives, anyone who will listen, there we have an outreach training session next week on Tuesday at 2 p.m. The link for that is also in the chat. Feel free to register if you'd like to learn more about some of the activities you can do and dive in deeper and have more of your questions answered should you still have them. Jean, Natalie, thank you again so much for this fantastic talk. And we look forward to hearing from you how everything goes down in Kourou, and we can't wait.
Awesome. Thank you for the platform.
Yes, thank you so much for the invitation. It was great. Thank you for everybody for listening and for the questions.
All right, we'll see you all next